So today's talk, Jesse asked me to try to tie together the modeling with what we've heard from several of the people, more like John Burge and Dennis Stroud, kind of their discussion of the water management issues when it pertains to surface water and groundwater. And so I'm going to try to tie those together with what we do for modeling out in the Panhandle. So I want to give some thanks to North and South Platte NRD. We do a lot of work with them out in the Panhandle. I've worked for those two entities since 2009, and so I've had a lot of experience out here dealing with their water issues, dealing with their data, which is very, very, very extensive. And so we also do work for Upper Navajo White NRD, which is the NRD to the north. I'm not going to talk about them in this particular one because we don't have time. I could go on for hours, which I think you guys are probably bored to death with. But I'm just going to touch on this and the Western Water Model. Name my speech, modeling to aid management systems in the Southern Nebraska Panhandle, where we try to really use data and modeling to help these NRDs understand what they have, understand what their management does, understand the effects of their management on the surface water system and groundwater systems of these particular areas. And so we'll just dig in. So John had mentioned this in his presentation, the Western Water Use Management Modeling. It was a model commissioned by North Platte and South Platte Natural Resources District and Department of Natural Resources. Has three models: a surface water operations model to dealing with the prior appropriation systems out here. A regionalized soil water balance model, basically dealing with crop water use, recharge, that sort of thing. And the groundwater model, which basically deals with flow and through the aquifer systems and stream flow in reality as well. What we try to analyze here, in reality, it's not as pretty of a schematic as John or Dennis had, but I kind of made it myself because it really had to be somewhat made because we have such a unique system out here. We really try to understand anything from precipitation, evapotranspiration of the crops, irrigation efficiency recharge, agricultural pumping, municipal industrial use, what happens with the groundwater system, direction of flow, groundwater movement into rivers and streams, groundwater, surface water recharge out of canals. And then we have to deal with all the subsurface stuff. We have to deal with the alluvial material, the river stands and gravels that make up a lot of the North Platte River aquifer, some of Lodgepole's aquifer, some of Pumpkin Creek's aquifer. There's a lesser known aquifer system out here that doesn't get talked about a lot. It's very important to Pumpkin Creek, Lodgepole Creek, and the North Platte River Valley is the rural fracture aquifer. We have a fracture system aquifer out here as well. My house well is a fracture system aquifer. My stock wells are fracture system aquifers. And so you get outside of these alluvial sand and gravel areas and you have other style aquifers that we have to deal with and understand. And that's one of the lesser known aquifers and really don't understand the orientation very well, how it's formed, how much of a fractures are there, but we know it produces water, we know where they are at the very least. Kind of thing. So these are the kind of things that we try to model, in essence, through our computer simulations. We go from May 1953 through December 2020. That's our modeling time frame. We just did a recent update to get through December 2020. We kind of deal with this model on monthly time steps. You can kind of choose the time steps that was the most reasonable for us. Lots and lots of different data sets that we have to deal with. One of our most extensive is land use, because if you don't know where your water's going, you don't know where you're applying it, you don't know how you're using it, you really don't, there's no point doing the model. So we really, really focused on land use, a big focus on geology and hydrology, of course, focus on understanding the surface water system and groundwater information among many, many, many different data sets. So I'll touch a few of those today. But again, because land use data sets are so important to us, this is kind of my first slide here showing how we analyze and how we characterize land use in this area. And so this is basically land use development here. These different polygons, this is would be a typical flood field in the area. The round circles are obviously sprinkler pivot irrigation out here. And then you can have different crops in any one of these pivots, or a combination of crops in any one of the pivots. So we have to know not only how it's being irrigated, whether it's sprinkler irrigation or whether it's flood irrigation, but we also have to know, it's crops. There could be 3 to 4 crops per pivot. So we have to know how many crops are on each pivot to know what water use is out there for each pivot. So we have lots and lots of information that we have to gather and put in this so we can understand the consumptive use standpoint. You heard some discussion of consumptive use. Steve talked about it quite a bit. You know, how much water does a crop use and evapotranspirate out of the system. This is then, you know, this is a zoomed in look. This is a large scale map on the bottom right corner here showing the red's the irrigated area, the yellow is the dry land cropland area, and the gray area is everything else. So it's pasture land or whatever area. And some of these yellows even probably represent pasture land, but kind of shows you, at least on the irrigation side of things, where all the irrigated acres are. And we've had some discussion on that. The economist talked about that earlier today. But this is kind of more of a map showing, at least in the southern panhandle, where all the irrigation is. And you know, you can see spatially here how Scottsbluff County, which is this county right here, and Morrill County, which were one of the two biggest counties, have most irrigated acres ever. And that's mainly due from surface water irrigation and groundwater irrigation, that combination of the two. And so, kind of maybe hopefully put it in perspective. The southern panhandle, which South Platte NRD encompasses these three counties down here, you can see they have a smattering of irrigation in the Ogallala aquifer that's up here on the tablelands, and then along Lodgepole Creek, which is a creek that appears and disappears as you move up and down the stream. So kind of just give you an idea of the land use and the importance with it. And so we do lots and lots of work with understanding the irrigation type and the crop types, and then we do this about every other year. We look at aerial photos to determine what irrigation has changed throughout the year. Kind of go to some of, I think John made some points about irrigation efficiency, and so did Dennis, and we had that discussion early on around the economist when he was talking about irrigation efficiency. So we try to really understand how irrigation efficiency played a role. This is some of the crop statistics that we have. This goes through 2013. I haven't done my 2020 data sets yet. But showing the different proportions of crops. And so somebody had a question earlier about sugar beets. And so sugar beets is this little itty bitty piece of this graph here on top of North Platte NRD. So that's the portion of sugar beets. So it's a pretty small portion of sugar beets of the whole. The majority of the crop is corn and alfalfa in reality. And so that's where most of our crops lie. South Platte NRD, very similar. You can see trends through time. 11, 12, we had a pretty high corn price, very, very, very high corn price, I should say. So you can see good bump ups in corn prices here, reduced down in alfalfa amounts, and so you can kind of see those commodity prices through time in the land use data set. Irrigation efficiency, that's this top graph here, kind of showing trends of irrigation efficiency through time. The bottom solid line is surface water irrigation efficiency. The top line is, and the top line is groundwater irrigation efficiency, which is basically rose as new pivot technology came on and been pretty steady ever since. The surface water irrigation efficiency is a bit different. It's hard to characterize because they have a lot of water, so they can over-apply and drive their efficiency down, though they're using more efficient techniques like pivot irrigation. And so there's different efficient components that we try to track, but you can see, increases in efficiencies in any year, but also you see decreases in efficiency when they have huge water supplies. So we have lots and lots of water, we apply all that water, but we just don't necessarily need it with the crops. So you get kind of these efficiency changes throughout time. So unfortunately, it's not a really easy thing to tease out. In reality, we have a variable amount. Groundwater pumping's here on the bottom, showing North Platte NRD groundwater pumping, and since 1953, what the groundwater pumping in the modeling looks like. In the model, the wells in the area, this is a lot less density than you get in eastern Nebraska. There's a lot more wells in eastern Nebraska than there are here. But you can see in general, like the north up here, the Box 2 County area up in Iowa White, you see a high density of wells. You see the valley have a high density of wells along Pumpkin Creek here, the lower part of North Platte River, along Lodgepole Creek, the tablelands, and then along the South Platte River and out the tablelands south of the South Platte River. So kind of showing in the modeling where we have all the wells. Somebody asked about a good map for the Canal Districts. I don't remember who that was, but here's my map for it, showing different color scheming of the 26 canal companies in Nebraska. They're kind of showing along the North Platte River where they're located. There's more in Pumpkin Creek that I did not show, but they're really small, so you can't see them. And then there's, we also deal with a little irrigation district down here in the modeling along the South Platte River called Western Irrigation District, and so that would be right up here, and that's this zoomed in map here, south of Lake McConaughey for South Platte Natural Resources District. Diversions, kind of give you guys an idea what the diversions look like in the North Platte system. About a 1.2 million acre feet is diverted in any 1 year, so it's a lot of water that we divert and bring in from the reservoirs or divert through natural flow processes and whatnot. It's more than the storage. So, but you got to realize that we diverted water for so long, we have all this return flow, so then all the downstream canals divert return flow back from the river, and so we get more water than what's in the reservoirs to the west. So that's just kind of a schematic of that. We have to deal with weather stations and climate, and these are not all the weather stations we deal with. We have a bunch of new ones John mentioned. Soils, different kind of soil properties to understand infiltration, recharge, evapotranspiration, evaporations off the soils, those kind of things for different soil types. This is the modeling we use. We use a modeling called Microsix. It's a really new model software, at least typical for groundwater modelers. A newer model software last 3 or 4 years it came out. We have variable cell sizes from 2.5 acre cells to 640 acre cells. So we go from tiny to about 1 mile by mile cells. So this is all brand new. We just kind of implemented this recently. It helps you make your creeks look like creeks instead of just a big blocky signature of where the creeks are. We kind of get to define that and become better at understanding the timing and flow of groundwater through the modeling. There's lots of stuff with saturated thickness. These are our updated saturated thickness maps. So knowing the base of aquifer and the geology and how much water we have to deal with, which helps us with understanding the rate of flow. The recharge, this is a recharge map on the bottom, kind of showing where the locations of recharge are. And you can see the canals, which is kind of striking in there, of where we've estimated the recharge in this model, and then the geology, where we have alluvial material, river sands and gravels in the North Platte Valley. We have Ogallala flanking it on each side, but you have the Ogallala cut down by the North Platte River and Pumpkin Creek and eroded away, which goes to John's discussion about the alluvial material. We don't have a huge aquifer like you get in the eastern part of the state. Though we do have a lot more aquifer down in the Ogallala areas, north and south of the North Platte River. And this kind of shows the calibration of our modeling, water level calibrations and the surface water calibration that they are draining. So that was kind of model background, and I wish I could go more because I got a lot more, but I'm seeing sleepy eyes already. Robust review is one of those analyses that we had to do. North Platte and South Platte are obligated to their integrated management plan. John touched on your integrated management plans in his discussion. And so the robust review analysis really helps us understand what has happened, how much. So one of the things the NRDs have to do, they do this robust review, but they also have to understand how much post-97 depletions occur. So how many acres came online after 1997, and then they're obligated to reverse those acres, or reverse that depletion from those acres, and put back in that water and more if they can. And so we had to look at that for the robust review. We kind of used all the data sets I mentioned just before this, and I'll kind of get into the graph. So this is the graph of that, kind of a nondescript graph. And I'll kind of step through it so you guys understand what we found. So first of all, we found that post-97 development created about 7,000 to 8,000 acre feet of depletion along, this is the groundwater only lands. So those lands are only serviced by groundwater only. Since, whoops, that was a mess up. So these are the 97 land use development. So you can see this yellow line, this yellow bar here represents 97 levels of development here. So that's the acres over time as well since 1997. This coincides with the amount of depletion or the amount of water taken out of the river since 97, which amounted to about 9,000 acre feet, or 7,000 to 9,000 acre feet. So that was what they had to mitigate. Then we've had allocations come online. So the district, North Platte NRD, this is the North Platte NRD robust review. I have a South Platte one too, I'm going to show. But North Platte NRD implemented allocation. John mentioned 70 acre inches per year for 5 years in the North Platte Valley, 60 in Pumpkin Creek. And so this is the effect of allocations. So they've gained a huge amount of water in a very short time by implementing those allocations. Upwards of, well, if you take and add up the mitigation of the 8,000 acre feet, they've added nearly 30,000 acre feet of water to the river in a few short years, based on, in part, on allocations. We have a 2011 excess flow event here, so this is 2011. In that year, there was so much water in the system, they diverted water, they recharged it through the canals, and we got credit for the excess flow water, which came to mitigation of these depletions that we see here. We had a whole bunch of groundwater only retirements, and showing the groundwater only retirements through time. And so how many acres that John had mentioned, it's very expensive and it can affect tax rolls, but this is what the NRDs have retired through time. Since through 2013, about 3,141 acres. And then in other kind of more, I suppose, just by over time, the irrigated acres have actually decreased in this area. Just through the fact that they either well dry up, they just was marginal land, they couldn't farm it, just a whole bunch of factors meaning that they don't irrigate that land anymore. And so that's kind of showing some of that, reduction. And then you see this kind of curve in there where it's not a straight line from there to there, because groundwater systems take time to react with surface water systems. So this is showing a accretion map from some retirements that we've done, showing how fast they can be or how slow they can be. And these were all in North Platte, these both were in North Platte NRD, so this is a very fast reacting system that you got 80, 90%, and then a few years where this one took, I don't know, what is that, 50 years to get to 70% based on the modeling. So we have these systems that are reacting, the surface water systems are reacting from a very long-term groundwater retirement, so removal of those acres from groundwater. So you get that kind of curved look from there. But in reality, kind of what we talked about before, the NRD has done an amazing job of not only mitigating their depletions, but going well above and beyond that amount, which now I think, we're kind of stuck with that now, John, aren't we? That's our new target, is to maintain this 25,000 acre feet of accretion back to the system in any 1 year above the post-97 depletions. And so that's a lot of water that we put into the system.
You're welcome, Twin Platte.
What's that?
I said you're welcome, Twin Platte.
Yes, and welcome Twin Platte Central Platte, get the benefit of that, which is fun. So I'm going to completely switch gears for me from surface water management. So that's kind of what we found through robust review analysis to help this NRDs know. South Platte's in a similar situation. They've had a lot of good, they have limited allocations as well, have had a lot of good accretions back to the system as well with this. And so the other thing that we deal with a lot, this kind of goes more to a South Platte Natural Resources District analysis and aquifer life analysis. That's kind of my own self-made term. But really, what is the aquifer life? A lot of these districts didn't know how long these aquifers would last in some areas. And so we have done aquifer life analysis in these, and I'll explain what that is in a second. But the areas of focus was this northern tablelands aquifer, which I won't talk about in this analysis. I'll kind of focus more on this southern tablelands. So here's Wyoming. Here's the Colorado border. Right here, this red area signifies the tablelands kind of analyses that we did. And really, it's helping provide North Platte, South Platte NRD with information on what's the future drawdown and what's the potential future drawdown, potential future saturated thickness of these aquifers. And then a secondary objective, which was my own objective, is trying to facilitate discussion, because nobody knows how to approach this stuff. You know, how do you manage these deep systems for these kind of aquifer declines? And we're talking Ogallala, we're talking Arickaree aquifers, these deeper aquifers out there. How do you get the public engaged? How do you get the board? My challenge is getting the board engaged and understanding and helping me understand what can be some management if they want to have management in those areas. Things we have to kind of realize in these areas, our recharge out here is very, very small. On average, we get about a 1/4 inch of recharge. It's not very much. That's all the recharge we get on very long-term averages. We have very small amount of rainfall, and we have lots of grass, and grass is really good about taking water up quickly. So we get very, very little recharge up here. You can think about more of this as more of a mining situation, if you will, where you're pulling groundwater out and you're mining it out of the groundwater. And then, you know, I don't like to say sustainable pumping. I think you got to really think more about it as some sort of managing groundwater declines, what you're really trying to do out here in these areas. And that kind of goes to these last 2 points I have on the board. So how do we do this? We took the last model head, so in the model you get a head or an aquifer level, and use last model. We ran it for 500 years, which is ridiculously long. And we did that for a couple of reasons. One, because we need to understand if these aquifers ever dry up, how long will it take if they dry up? But we're out in kind of a really, really long time, so we're kind of assuming a lot. We're talking about the assumptions of the economists. Well, that's nothing compared to a geologist, because we have to assume things on such a longer time scale. So I guess I'm touting more assumptions, I don't know. And then we have to use some sort of climate scenario, and that's the hard one. That's the assumption that makes it very difficult, is what climate do you assume? And so we ended up with a lot of these areas as assuming the last 5 years, which was allocated. Because if you assume the last 25 years of climate or something like that, you have allocated, non-allocated periods, So we ended up to be more palatable to the public and the boards of just assuming the last 5 years, which ended up being a pretty good average. We did some statistical analysis to make sure if it was average or above or below, and it was decent. More data is always better, but it was the best we got because it was during the application time where the limited pumping occurred. And we look at results of drawdown and percent saturated thickness used, which I'll talk about in a second. So then running the simulation forward for so many years and using a repeated cycle of whatever climate and assumed pumping, we get certain maps, and this is drawdown at 100 years. So in the southern tablelands area, in 100 years, 25 to 50 feet of drawdown. You know, it's interesting to see kind of what the results, based on the geology, our understanding of the geology, understanding of pumping, climate, all that kind of stuff, what that ended up being. And this is repeating 2012 through 2016 over and over and over. Then we ran it at 500 years, and I'm giving you these two. I have all the data points in between, but these are the two I'm trying to discuss. This is at 500 years, and we're looking at, you know, 125 feet of drawdown, 50 feet, 75 feet, lots of drawdown in these areas. And we kind of have to realize that's a long time from now. 500 years is a long time from now. But these are what they wanted to understand, and we wanted to understand that in general just to see what would happen. So then, but then here again, what does drawdown mean? 125 feet, well, who cares? What does that mean? So we put it into different terms, and we did a percent saturated thickness use. So if you have X amount of saturated aquifer material below your feet, what percentage of that material are you going to use in any 1 year? So instead, we said, okay, well, in 100 years, how much of the saturated material that we have, that we started with, are we going to end up with in 100 years? And you can see some of these areas are going to be 75 feet of saturated thickness is going to be gone, which effectively means they can't pump anymore the way they're doing now. They have to change types in these certain areas. And so you can kind of see how that changes. And then if you look at 500 years out, you can start to see when you start to impact and basically take away pumping in the entire panhandle, or southern panhandle, in these deeper aquifers. Based on this climate and those huge assumptions that are way more impressive than the economists' assumptions, in my opinion. Anyway, so that just kind of gives some ideas about that. So that's just the data side of things. And then, you know, these are my questions to the board and to the public is, you know, if we're going to talk about aquifer management, we have to talk about it in some terms. So how far in the future do we want to manage for this? I mean, do we want to be a couple generations of farmers in the future managing for these groundwater declines? Do we want to be 20 years? Do we want to be 500 years? Do we want to be 250 years? How far is the management going to be in the future? And then likewise, what is the acceptable reduction in that time frame? So if they want to start reducing the amount of their pumping in any 1 year down, they have to answer these two questions to help them understand, are they going to be, how much are they going to be impacting it, and when are they going to impact it, and how long do they want to manage it? And that's a very hard question to answer. I don't know what the answer is, but that's just an answer. I think they need to come up with these two questions here. And we did a survey, and so the most likely, how much in the future would you like to manage was 200 years. That's what people in general said. They want to manage for a couple hundred years in the future. And people, and I think it was 50% of an aquifer decline was acceptable to them, so over 200 years they could take 50% of the aquifer decline. Some people said, we don't give a crap, we want to take it all today. Some people said we want to manage 500 years in the future and we don't want any drawdown, which is also unrealistic. So there has to be some interesting, realistic management questions and thoughts with this kind of stuff, which gets hard, and these are opinions, these are just basically what people want to do with this kind of thing. So, because it's more of a money type situation. So those are two examples of the analyses we do. I have hundreds more, but this is what I had time for today. So if you guys want some more information about the Western Water Model, I have the Southwest website. I think Northwest has the same thing on their website, but a lot of the groundwater, a lot of the modeling documents, a lot of the documentation is on that website. The models themselves are out there as well. So we have all this information out there for people to grab if they want to look at it and have some good nighttime snooze reading. So thank you.
We're going to switch over here, so give us just a minute. I'll stop the share, and then JP can.
You're going to do questions after?
Yeah, we're going to do questions at the end. So next up we have JP Trailer. He's a hydrogeologist, or hydrologist. I don't know how much geology you do. So he's just a hydrologist at the U.S. Geological Survey, so we still get the geology, at their Wider Science Center in Lincoln. He received his BA in Geoscience from Hamilton College in Clinton, New York in 2010. He received a Master of Science degree in Earth and Atmospheric Science with a concentration in hydrogeology from UNL in 2012. JP's been working for the USGS Nebraska Water Science Center since 2012. JP's focus as a hydrologist in the USGS is groundwater flow modeling, and he specializes in the development, construction, and calibration of groundwater flow models using the latest software and techniques developed by the USGS for use by water managers and stakeholders. He's developed or assisted in the development of groundwater flow models in Nebraska, Oklahoma, Texas, Mississippi, and Arkansas for multiple parts of the High Plains Aquifer, the Mississippi Embayment Regional Aquifer System, and the Coastal Lowlands Aquifer System. Welcome, JP. Hold on. JP, you are still muted if you want to take yourself off of mute.
Okay.
There we go, we can hear you.
I'm going to share my screen now. This worked earlier.
Yes, we're seeing it. If you want to put it in,
Yeah.
there we go.
Just take a second here. Okay, thanks everyone for attending. Thank you to Thad for presenting. It was a nice presentation. And so my talk is going to be centered around kind of this past and present theme, how we used to do groundwater flow modeling, and I'll have a summary of a groundwater flow model that was developed by our current Center Director, Steve Peterson, back when he was the lead groundwater modeler for our office. It's the North Platte Optimization Model. I'll briefly talk about that and kind of what was done there. And then the second part of the talk is focused on the latest software and techniques that we use here at the Nebraska Water Science Center and the USGS to facilitate construction of models and calibration and analysis of those models. So just an overview of the North Platte Optimization Model. This study was conducted mainly from like mid-2000s to about 2011, 2012. They had some management interests associated with that, with the integrated management plan, complying with the cooperative agreement, and the kind of focus of wanting to try to understand how to improve base flow of North Platte River by maximizing the benefit of their intentional recharge or managed aquifer recharge. And of course that has a lot of downstream surface water availability implications because the North Platte NID is the farthest upstream in Nebraska, particularly during the irrigation season and under varying climate scenarios. Here's the picture of the report that was published for this study. So like I said here, the study area for this model was the alluvial aquifer in the North Platte NID. Circled in red, and you can see that the large arrows are locations of major surface water diversions downstream. So like I said, any management decisions that occur in the North Platte River have big implications for surface water availability downstream. So one of the big things with this study was the collection of a lot of airborne AEM data, electromagnetic data, to update the aquifer base. This model was one layer. So the base of the aquifer was the bottom of the model, and so coming up with a better interpretation for that is crucial in developing a more accurate model that would provide more accurate results. So you put all the data together. It was collected, which included the AEM data, the canal resistivity data, plus test holes. You can see the North Platte River downstream in the top right. That's the direction of flow downstream. You can see all that data put together. Fence diagram, you can notice the warm colors are sand and gravel, cool colors are silt and clays. And this is an example of a 2D cross-section for the old versus the new aquifer base that was in the model. The black line is the old one that was developed by Coheis, and it's interpolated between test holes, which is, there's nothing wrong with that, it's a good aquifer base, but there's a limited number of test holes, and the AEM data, which is the darker, like the brown color, you can see with all the erosional channels and all the detail, different saturated thickness of the aquifer, all that stuff help improve the subsurface characterization of the model and the aquifer. Canal leakage, like I mentioned, was an important aspect of this model. The NRD wanted to know where they could put intentional recharge that would flow quickly to the Platte River to support base flow, and also where they could potentially restrict some pumping of wells to affect stream flow. And of course, the route and rate of turn flow of that recharge to the river was something they were interested in. The canal resistivity was a surface resistivity survey, and that data went into the model and helped better simulate the model, or simulate the canal leakage, because the canals are kind of heterogeneous in their leakage, where you can see this figure here, the warm colors with the big circles indicate more canal leakage across an irrigation season, and the smaller green circles indicate less leakage across an irrigation season. This, like I said, all this is going towards, all this data collection is going towards a more accurate model. So here's an example of a calibrated stream flux at the North Platte River gauge at Bridgeport, measured for simulated. And then another aspect of this was the optimization part of the study to use this model. And so optimization, just a background for those of you who aren't familiar, optimization is where a model solves for optimum or best combination of decision variable values while meeting some goal or several goals. And these goals are the things that you want to optimize, either minimize or maximize, while meeting some type of constraint, which is usually a water level or a stream flow, held like above or below a certain value. In this project, it was to minimize intentional recharge and maximize groundwater withdrawals, because the surface water diversions to use for intentional recharge cost money. And the constraint was to keep stream flow and base flow above a certain level. And decision variables, those are actually just the model parameters in the optimization. Those are things that the optimization code actually can adjust. And from a management perspective, that's the management tools that the NRB can use to apply to their management scenarios and rules and regulations. And in this model, the decision variables are the amount of water pumped by wells in each well management zone, the NRD outline, and also the amount of intentional recharge at each site. And further, you can add constraints and optimization on the decision variables. And what that means is, for example, in this optimization model, they're limited to the reduction in pumping to 50% of the crop irrigation requirement. That way, they're more useful optimization results. It wouldn't be that useful to the cooperator if the optimization result came up and said, oh, well, if you pump zero, if you don't pump anything, then you'll have a lot more base flow. It's like, well, then nobody's going to be able to irrigate their crops with their wells. So I have a useful optimization result. You can apply that constraint limiting the optimization above 50% of pumping. And this was all done with what's called GWM. It's a groundwater management process package that's linked to ModFlow. And this model used at the time the latest developed ModFlow software, which is ModFlow Newt, to solve for the unconfined situation. And that's kind of the old way of doing things now. And I'll talk later in the talk will be the new way we do optimization. Here on the left are those well management zones. And the numbers there, acre feet per year, the average maximum pumping for all the wells in each zone. So the optimization was limited to reducing that by half, all the way up to the full amount. And then the intentional recharge sites, which were selected using various data sets, trying to identify sandy areas that could facilitate recharge to the aquifer that would flow near canals that would flow to the North Platte River. Those sites are in red. And the results of this optimization are in this table, and they ran it for 3 different precipitation conditions: wet, average, and dry periods. And 3 different scenarios are kind of plotted here with the max vapor management situations, where there's max base flow at full pumpage, so that's 100% of that crop irrigation requirement. You'd have base flows plotted here. And then with a reduced amount of pumpage, There's another set of base flows for the precip conditions, and then you have the max base flow that would be attainable with reduced pumpage plus that additional intentional recharge. And then, so you can see that there's a working range of base flow the system's capable of, and the infeasible column would be with the current constraints of the model, with like limiting pumping to no less than 50%, and then max recharge, intentional recharge rates. The feasible range there is something that the system couldn't produce. And just to summarize, this was like a team approach. There was a lot of people involved with this, all the way from like the surveying of the AEM data collection, the modeling, working with the resource managers, the NRD, to come up with a useful tool. There was geophysicists, geologists, hydrologists, the modelers, and the NRD managers. All came together to produce kind of an efficient workflow that was useful for the NRD. And the AEM data had a lot of sponsors here that I'd like to acknowledge. So that was a project that was, most of the work was done over 10 years ago, and so there's been a lot of advancements in modeling, specifically within USGS. So I'm going to discuss now kind of our latest techniques and methods that we're using. And so this is for myself and my colleague, Musa Gira, who we're both lead groundwater modelers in the Nebraska Water Science Center. Some of the stuff that we're involved with today. And so with that, I'm going to talk about something we're working on with a project in the Mississippi alluvial plains and lessons that we've gained from Nebraska. So this team approach, the techniques and methods that were kind of used in the multi optimization model, we've sort of been using that kind of workflow in this Mississippi alluvial plain study. Modeling study that we're involved in. So characterization of the subsurface with the AEM data, integrating that into groundwater flow models, and then we're doing that stuff right now, and then I'll have some examples, some optimization modeling for management that we'll be doing later. So thank you to the North Platte NRD and other stakeholders who were involved in that North Platte optimization model for investing in like the latest science at the time, providing like a framework for kind of a workflow and an example for other parts of the country to follow. Just a little background on this Mississippi alluvial plain study. The map on the right, you can see that the study is in the southeast United States. There's some similarities to Nebraska, and it's a densely irrigated, for groundwater irrigated for cropland, specifically in the Mississippi alluvial plain, which is outlined in black. So large groundwater withdrawals for irrigation, managed aquifer recharges occurring in the yellow box there. And the models that myself and my colleague Musa are working on are shown here in these boxes, and they're inset models of higher discretization, which will be linked to a larger regional groundwater flow model that simulates the blue domain. And we're using the latest Microsix software as well. So with the latest in techniques theme of this talk, the outline of, we're going to go over some of the ways we're incorporating the AEM data into groundwater flow models. I'll talk about calibration and the latest suite of pest tools that we're using, specifically Pestplus. If someone's familiar with the pest parameter estimation software for calibrating groundwater flow models, there's Pestplus now, which has some really cool stuff. Uncertainty analysis, and I'll talk about why quantifying that can be useful for modeling, analysis, and results. And then I'll talk about how we do optimization modeling today. So integrating that AEM data into models. In this Mississippi alluvial plain project, what we're doing is taking those surveys, and by the way, this was the largest, most amount of miles flown of AEM data in the continental United States in the history of the USGS. So it's a really big AEM survey. There's all the flight lines. There's even a high resolution survey that's in the inset there in Mississippi. So you get these AEM surveys with, and this just shows different depths of the data. And you can see the colors change because the formation's changing, the depth of resistivity changes. And you're familiar with, some of you may be familiar with plots like this, a cross-section of the, like I showed in the fence diagram earlier. You can see the different formations and different sediment types that relate to hydraulic conductivity. It's resistivity plotted out. So for the new optimization model, they took this and they delineated a new base of aquifer. Or you see all this different pockets of higher resistivity, hydraulic conductivity, higher resistivity, which is related to hydraulic conductivity. And so we wanted to preserve that detail and include it in the model. And so this is actually a picture of a 3D picture here, taking the AEM data and adding it to my colleague Moose's groundwater flow model in Mississippi that was in that little yellow box. It's called the Shell Mound model. And this is actually, we're doing this same technique for the models that we're involved in, myself and my colleague Moose. Basically, we're taking that AEM data and just using that for the vertical discretization of the model, and it's 5 meter constant thickness layers, which is a departure from traditional layering, vertical layering and modeling, where you would outline a surface, much like hydrologically connected, kind of varying thickness throughout the model domain, kind of, and produce like a surface. This is just 5 meter constant thickness, and each different color represents a different resistivity, which correlates to hydraulic conductivity, and that's not a trivial thing in and of itself. But this allows us to preserve, the detail from the AEM data in the modeling, and then makes for a more accurate characterization of the subsurface and the groundwater flow system, which is one of the salient points that we try to strive for in our models. And here's another example. This is the same thing, except we have varying model layer thickness with depth. This is a different model that I'm working on also in this Mississippi Alluvial Plain study, where the focus area is the alluvial aquifer, so it's shallow part. The first 8 layers are 5 meter thickness, but where we don't need as much vertical detail, we have increasing thickness layers. You can see at the AEM, the different colors of the AEM data, resistivity still preserved. And then where the AEM stops at the bedrock, we have the bedrock subcrops here. So calibration techniques. So I spoke about pest and parameter estimation software. So that's the traditional way of doing things, which we've certainly done in the past. I've used that for several models. And some of the things about that is there's a limited number of parameters you can specify because in order to do a calibration, it has to do one model run per parameter in order to calculate the sensitivity to the observations that you include. And that builds like the sensitivity matrix, is just part of the Jacobi matrix, and that takes a long time to do. If you have thousands of parameters or hundreds, and the model runtime is could be fairly long. So that basically adds up to long calibration runtimes. That North Cloud optimization model had some calibration runtimes were up to a month, which is it's typical with traditional pest calibrations to have calibration runtimes of 2 weeks, 3 weeks, and so that can really limit kind of the number of calibration runs that you have. Uncertainty analysis also is a separate task for traditional pests. The latest thing that we're using is what's called Pestplus plus IES. It's a derivative ensemble smoother. What's cool about that is that it has a unlimited number of parameters, much shorter calibration runtimes. So we've done calibration runtimes in this project on the order of less than a week, on sometimes 1, 2, 3 days, which really facilitates calibration. You can run many more calibrations and kind of dial in the model a lot better. And our uncertainty analysis is included in that as well. And so I've been kind of mentioning uncertainty analysis a little bit. One of the reasons why that's can be useful in understanding your model better is because there's not one acceptable value for, let's say, calibrated hydraulic conductivity at a certain point. you have a model that calibrates hydraulic conductivity at 25 feet per day. Well, maybe you would have accepted 22 feet per day, or 32, or 33 feet per day. And that range is an uncertainty in your model inputs, which is typical in modeling. And that uncertainty in your model inputs transfers to uncertainty in your model outputs. So that's going to, each one of those different hydraulic conductivity values is going to give you a different water level or stream flow in that area that may also produce an adequate or acceptable fit to the measured data in that area. So you can see how there's some uncertainty in model results. And you can use that in optimization as well, which I'll talk about later. So the benefits of more parameters is really that, like I've been saying, the reality of modeling is that there's just not enough, there's never enough data, there's never enough test holes, there's never enough data per model cell. So that creates an imperfect model structure, a lot of unknown inputs. And so assumptions are necessary in modeling. And the more parameters you have, that better allows Pest to adjust everything to find an optimum fit. And it also allows for the model a better characterization of that model's imperfectness or uncertainty. So not parameterizing an uncertain model input falsely equates to 100% certainty of that input. And that can lead to bias in the results, and that's something that we're always, the USGS here during calibrations, we're always trying to limit the bias, especially with the keeping in mind the objectives of the model, the questions it's trying to answer. So what are we talking about with different acceptable values of hydraulic conductivity? So this is a plot of calibrated hydraulic conductivity with this Pestplus IES software. And you can see that like zone hydraulic conductivity zones 1 and 2 here are examples. This is a histogram of 500 different model runs with different combinations of parameters, very much like a Monte Carlo run. IES is basically like Monte Carlos with different parameter upgrades per iteration, if you're familiar, and I'll show you a plot next to that. But you can see that where there's more likely, the red line is centered around the more likely values. The count here for the histogram indicates that this hydraulic conductivity values around here are more likely producing a better calibration. And the ones as you get farther out, those are producing a less good fit to the data. And so you can see there's a more likely, less likely kind of value for hydraulic conductivity for this parameter. And each one of these values will give you a different water level or stream flow. So here's what IES looks like when you get some results. There's a bunch of black lines on here, and the x-axis is the iterations. If you're familiar with Pest, it makes parameter upgrades, goes through another iteration, learns from the measured data, makes more parameter upgrades, and continues on. The y-axis is the fit to that measured data. The objective function is phi. It's called phi in Pest, or Pestplus. And so you can see that you start out with initial runs here. There's 500 black lines and 500 different combinations of parameters. And IES runs and improves the fit between those with the measured data. And you can see the shrinking distribution of those parameter values basically improves the fit to the data on all the model runs. So you actually see the uncertainty of the model results go down when you see that everything's tightening up. The blue line is the base run, that's your initial values, and that's the path of the calibration with your initial specified values. And we keep doing this for as many iterations as you want, all the way down to the bottom. And obviously there's something called overfitting that you have to be aware of in calibration. So it's the best fit to the data. The measured data is not always like iteration 6 here. This is the lowest number, so best fit. This is maybe not always the best set of parameters. Calibration involves an acceptable fit to the measured data and acceptable values of parameters. And so just to summarize with uncertainty analysis, the standard deviation of the model outputs result from an ensemble or a bunch of different combinations of model input or parameter values is the model uncertainty. You have uncertainty in your inputs and as well as your model outputs or your model results. You can see here, this is the output, the uncertainty of the model results, and this is the uncertainty of the model inputs or parameters here. So that kind of goes to show that data collection is very, very important for modeling. The better the model improves or learns from in calibration, the model learns from the measured data that's included in it. So, the more measured water levels, the more accurately measured water levels and stream flows that you can, and other measured data you can put into a model, the better calibration you can get, and the less uncertainty you're going to have in your model. So that goes towards, always better, more data collection. Optimization, I'm going to move on to that now. Here's an example of an optimization for a problem that we simulated for this project. Basically, it's a simple one, maximizing pumping while keeping the water level above 36 meters of elevation, sun elevation. Decision variables, those things that the optimization can adjust, are the pumping rates through time, and the constraint is just a simulated water level at an observation well. So in this tool called Pestplus Opt, short for optimization, you can turn observations into constraints, which is pretty cool. So here is the results. On the left is the pumping. The optimized pumping is in orange. The blue is the kind of the base pumping. And what you see here is you can pump a lot more sometimes, but also there's other periods here. If you look in the top left, you can see where it says you can't pump anything at all, and you're actually pumping a little bit in the base. So the optimization kind of says you can pump a lot more sometimes and other times not. The results of that orange pumping in the model, simulated water levels stayed above the constraint here of 36 meters, which is good. That's what it was supposed to do. But you may be asking yourself, well, you just talked about uncertainty a whole bunch. Does that affect optimization results? Since you said you could have different reasonable parameter values for hydraulic connectivity and other inputs. If you ran that optimized pumping value through those, what would you get? Different water levels, perhaps, and you would get different water levels. In this range here, outlined this light purple. So this is the uncertainty in the simulated water level at this location. And so what you'd see here is something interesting. The sum of the model runs with different combinations of acceptable parameters using the same orange line for optimized pumping value. They actually produce water levels below the constraint. So you're like thinking probably, well, that's not good. What are you supposed to do with that? And in this new SPP Opt tool, you can actually use risk assessment and combine that model uncertainty with the optimization in what's called this chance-based constraint assessment. So this is the same problem that I'm going to show here, the goal of maximizing pumping while keeping your water level above, let's say 36 meters of elevation is the same constraint. That could mean keeping the water level above the top of a public well water supply screen or something like that, as example. So there's this risk factor that you can set in SPP Opt, this new optimization tool that we're using. And you can set it, let's say you're risk averse, you're erring on the side of caution, you're a water manager, and you don't want the water level to go below this constraint. So you set this at 0.05, you run your optimization, it finds a pumping rate, an optimized pumping rate, in which 95 out of 100 of the model runs produce simulated water level greater than 36 meters, or greater than the constraint. So that's cool. What if you're risk neutral? Maybe it's not that big of a deal either way. Finds a new pumping rate. You set your risk at 0.5, and it finds a new pumping rate where the optimized pumping rate produces a water level where half of the model runs above the simulated water level or the constraint. Maybe you're risk tolerant. Maybe there's not really any consequences for a water level dropping below this 36 meter threshold here. And so you can say, we're risk tolerant, we set this risk dial up really high at 0.95, by the way the range is 0 to 1. Set this risk dial up pretty high, and it will find a new pumping rate where the optimized pumping rate simulates water only 5 model runs out of 100 with a water level above the constraint. So if you look at the pumping rates for each of these optimized simulations, A, B, and C, it's called Q well. The optimized pumping rate for A, the risk averse, is actually the lowest pumping rate, and Q well for C, the risk tolerant situation, is the highest pumping rate. So if you're if you're a manager and you want to be risk averse in your decision making and you add a pumping rate to your rules and regulations for this well, you would pick pumping rate for A. If you were risk tolerant, then you would pick it for the pumping rate for C. So that kind of concludes all of the stuff that I wanted to present. We'll just have some summary takeaways here in the past. There's this team approach that began with the Northlight Optimization Model, and we carried it on through to current projects we're working on with the collection of the AEM data, integrating all that data into groundwater flow models for improved characterization of the subsurface and more accurate models. We're always striving for that. Monthly Mute at the time, which was published in 2011, that was used to calibrate the model, so that was like the latest thing at the time. Now it's Microsix. GWM, or groundwater management process, was the optimization tool at the time. And now we're using SPP Opt and some of the new features of that. So the present part is that the USGS and the Nebraska Water Science Center continues to use the latest advancements in modeling to improve inputs, calibration, and analysis, and provide, with the goal of providing more useful models to stakeholders, and so they can make better informed, science-based decisions based on the latest science available. With that, we're using Pestplus plus IES to calibrate Pestplus plus Opt. Both these things were published last year. And Microsix now has been out for several years, but there's new developments that were linked in with the developers. They're coming up with new features, new tools all the time that we're actually using to facilitate model development, model construction. And the new approaches to the calibration aspect is that with the increased parameterization, I went over that. Efficient faster run times is always good. Quantifying model uncertainty can be very helpful for models, and then also incorporating that uncertainty of the model into risk-based management optimization can be useful information for managers. There's some references. I think they're recording this talk. If you want a list of these, I can give you these too as well. It's contact information. And I think we're going to do a joint question session now, if I'm not mistaken.
All right, thank you very much, JP. Let's give him a round of applause. We've used up.
I assume I should probably stop sharing.
Yeah, you can do that. That'd be great.
Okay.
We've used up most of our time, but since JP's online, I wanted to give you guys some time to ask him some questions. Thad's going to be around, so I thought what we might do is, if you've got questions for him, you can see him here throughout the rest of the day. But if you've got questions for JP, any questions?
I will ask a quick question, don't want to hold up everybody. So JP mentioned the Nebraska model was a motivation to do the Mississippi Environment Aquifer model. So
You're going to have to repeat that, I can't understand it.
So Nebraska model, what you showed before, the optimization model for the North Platte NRD, that was the motivation to do the Mississippi Environment model. So what is the similarity there? Is it same as alluvial system and also same issues they're facing with? Why it was the motivation?
Can you repeat his question, because I didn't understand one word?
Okay, I'll try to paraphrase. He was wondering about the connections between the North Platte model and the Missouri abatement model, and what are the similarities in the model? Because you talked about the similarities in the process. Are there also similarities in the modeling? Is that a fair?
So, then, yeah, as far as like the software use or the technical aspects, is that what?
No, the aquifer systems themselves.
So the aquifer systems are a little bit different. It's the Mississippi embayment regional aquifer system. Yeah, the aquifer systems are a little bit different. They get a lot of, there's a lot of losing streams, and so there's a lot of recharge from stream leakage, and there's a lot of groundwater pumping for crops, so they have a lot of water level declines because of the groundwater pumping that's started in similar time periods to Nebraska in the 50s and 60s, but big declines since the 70s and 80s, and that's caused losing streams to kind of leak a lot of water into the system. So I'd say that's like the biggest difference. It's wetter for sure. They get a lot more rain, but it runs off. They're getting 40, 45, 48 inches of rain a year, but recharge values are similar to central Nebraska, where you're getting the 2 to 3, maybe 4 inches of recharge a year. And the gradients are very, very flat. It's an alluvial plain, so the hydraulic conductivities are pretty high. They're 100, 200, 300, sometimes even 400 feet per day in the alluvial aquifer. The gradients are very flat.
Oh, thank you.
Similar to along the Platte River.
Very good. One more question back here.
Yeah, I have a question related to the first project. You used resistivity to characterize leakage of the canal. So what type of resistivity did you use? Airborne electromagnetic or land-based resistivity? And how did you link between resistivity and leakage of the canal?
Were you able to hear that one, JP?
No, Crystal, you'll have to repeat pretty much every question, I think.
Okay. This is testing my memory, which is maybe not the best way to do it. So, the first part of the question was the difference between, did you use the airborne hydraulic conductivity?
Airborne resistivity
Oh, airborne
or
resistivity.
land-based resistivity?
Or land-based resistivity.
They want to know the difference between those?
No, which one did you use for, which model are you?
For the canal.
For the canal.
Which type of resistivity data is airborne or land-based resistivity?
Right, so in the Mississippi alluvial plain study, the MAP study for short, there's not really, I guess I left out the difference between Nebraska's and not as surface water diversions for canals. So they actually did waterborne resistivity to actually survey the hydraulic conductivities or the nature of the connection to the aquifer with on different streams. There's not really that many canals or anything in those areas. As far as like the difference between AEM and canal surface resistivity for canals, I think it's just the depth. I don't know the details because I don't actually conduct those surveys, but it's definitely the depth that they go to is different. The canal one's a little bit shorter, and the AEM definitely works best when you have finer grain sediments that are kind of sitting over top or underlying the underlying coarser grain sediments.
JD was asking whether it was airborne or land-based resistivity for the canal. Did you hear that?
He was wondering specifically, was it airborne or land-based for the North Platte canals?
It was land-based, I believe, but yes, they were land-based.
And then what was the second part of the question?
Yeah, well, what is the theoretical background between leakage of the canal and resistivity? So how could you, how did you use resistivity to characterize leakage? What is the link?
With the canals, what's the theoretical background between the resistivity
And leakage.
and leakage?
Well, I don't know the direct answer to that, but usually resistivity is, the higher the resistivity, the coarser grained materials. So you're gonna have generally more, higher hydraulic conductivity, more leakage is the general relationship with resistivity data. I assume that holds true.
Yeah,
But
because
that exact relationship
we could receive high resistivity. Yeah, we could receive high resistivity from many sources. You can have high resistivity from limestone, for example, or dolomite, which is no leakage.
All right.
So, yeah, we can discuss this later. Thank you so much.
He'd like to follow up and discuss some more of the details with you. But we are over time, so let's thank both of our speakers. Thank you.